Off we start. Okay, so today we'll do some geometry. We haven't done any geometry. Today's the one day we'll do some geometry, like low dimensional geometry, like shapes and stuff. So today, uh, I guess I'll introduce the additive Chernoff bound, which you haven't actually seen yet. Uh, but it's really about these things called epsilon samples and epsilon nets, and there's a very nice technique called double sampling. And we'll also talk about something called VC dimension that helps characterize the complexity of shapes. You might have seen this in a learning theory type of course before. Today I'll probably be coming at it from sort of more of a computational geometry point of view, but it has a lot of connections to learning theory as well. Next time we'll make the connection more clear. So next time we'll do pack learning. So okay, so in general, concentration phenomena is something like, if you have a bunch of little random variables and they're adding up to a large mean, then the odds of it deviating goes down exponentially. Okay? And at some level, it's very hard for lots of individual, small, independent pieces to kind of gang up to create a large deviation in the aggregate. Right? That's the general phenomena. The form you often see is something like this. The odds of being 10% bigger than the average if it's non-negative, it's exponentially small than the average, so on and so forth. Okay, there's 100 million variations. Now this one is going to be, so I should point out this is for multiplicative guarantees being off by 1%, but sometimes it's reasonable to think about additive guarantees. So I guess here's how I'll present it. Um, Let x1 to xn be, say, 0, 1 random variables. All that really matters is that they're bounded. Doesn't even really have to be non-negative. And okay, I'm going to sum them all up and look at their average compared to the mean, plus like epsilon. Okay, and you're going to get some guarantee that looks like something that's going exponentially small in the number of variables. Okay, so there's a couple of different ways to look at it. For example, I could take this n and move it over. It could be mu n and epsilon n. So the additive error is epsilon n, and now you're getting something that's sort of exponentially small in the additive error. So there's different ways to interpret this. Okay, so in some kind of case, additive doesn't sometimes make sense because it's not scale invariant, but in some cases when things are normalized, we'll see one such example today. Okay, it'll show up in the bottom right corner around the time we need to use it, so you don't have to memorize it. Okay. Oh, I guess here's a compare and contrast. Well, there's not much to say about it. Obviously, there's 1 plus epsilon times mu on one side. There's epsilon n on the other. Okay. All right. So I should note that non-negativity is really important for multiplicative stuff, right? But it's not really so important here in the additive regime. Okay. Good. All right. So we're really talking about things like triangles and points in space or something, or circles and points in space. And usually in low dimensional spaces today is the point of focus. But the way they like to codify this is they like to call it a range space. So you have some points and you have some ranges that represent subsets of the points. Okay. And today everything we'll be doing is over finite sets of points. Okay. But it could easily be generalized to kind of distributions of points and things like this, and none of the essential ideas would change. Okay, often learning theory prefers the distributional approach. Okay, so here's some examples. Uh, so just on the line in one dimension, you can have a bunch of points on the line and then intervals. Yeah, and so this interval here, induces a subset over 1, 2, 3, 4, 5, 6 points or something. Okay, so you have lots of different intervals. That would be an example. So the points are the points, the ranges are the intervals. Um, Okay, here's a colorful picture of some points points in space, the ranges are disks. Okay. One thing kind of interesting is that while we generally just kind of keep the points to be a finite set, uh, R can kind of be infinite. The set of ranges. This could be all possible disks in space. Okay. Although at some level we're kind of only interested in which of the points they capture. So there's only a limited number of kind of combinations of subsets it can induce over the point set. So there's kind of some implicit finiteness, but at some level we don't have to uh, impose it. Another one, this will come up a lot in learning theory algorithms. Is half spaces here. Of course, I drew it in R2, but it can easily be in higher dimensions, right? Sometimes classifiers want to say everything above one line is classified yes, everything below the line is classified no, something like this. Okay, so half space. So these are all kind of relatively simple shapes, right? They're all kind of defined by small, half space is just like slope and whatever y-intersect and things like this. Yeah. No, it's intended to be a finite subset of R2, a set of points in R2. Yeah, yeah. So R actually, yeah, I guess it's a little ambiguous. So here R can be any disk, and then the set of points will be finite. Yeah. It is helpful that the set of points is finite. And if you're doing infinite, everything will only kind of make sense if you're talking about distribution of points in R2, and distribution is very much the same as just finiteness in all essential ways. Okay. So okay. All right. So that's just this style that the geometers like to formulate things. They like to have these range spaces, points and ranges. And like imagine you're doing data structures or something in geometry or something. So they like to play various games. What do you do with a range space, right? So given a fixed range, I don't know. I can open it up. What questions or that you want to make data structures? What kind of questions might they answer? Of course, I don't remember which questions correspond to which colors. Yeah. Yeah. So how many points are in that range? I'm gonna go as number two. Somehow, okay. All right. How many points? It was number two, but I accidentally erased the first one too. Another basic question is just, is the range empty? Uh, and then another question is, how many points does it contain? Anyone want to go for the third one? Yeah. Oh, is a particular point in R? I think that we're going to just take for granted. Because that will usually just be some simple algebra. Oh, here's the center of the circle. Here's your point. There's a radius. Yeah. Yeah. What's the mass? It's pretty similar to how many points are in R. And yeah. How big is R? Uh, well, insofar, I don't know if we're actually gonna be interested in how big is R beyond how many points does it contain. Yeah. Uh, the third one maybe I don't. It's hard to guess, but like you might want to know like if R is significant for some threshold. You can do some heavy hitter type question. Which of the ranges are sort of heavy hitters? They contain at least 10% of the points or something. Okay, but you can imagine doing various games. And this happens naturally, right? I mean, I always give this example if you're placing cell phone towers or something, right? The cell phones are the points, and the towers that you can place, they're going to be disks or roughly disks. Yeah, doesn't contain any points. So we're really interested in kind of the point range incidence stuff. That's why I'm probably not going to be interested in how big a circle is in anything in this lecture, but I will be interested in, given this circle, how many points are in it. Okay, so that's just how they like to formulate things. Now, um, we can not to drown on formalities forever, but at some level we can also, besides counting points, talk about the percentage of points in the shape, right? And if you want to be fancy, you can call it a measure. What fraction of the points? Okay, but what we're doing nothing but for this range, how many points are in the range divided by total number of points? Okay, so nothing special. Now, imagine I took a subset of points Q. Okay. that'll induce another measure over all the ranges, right? What fraction of the points in Q does this circle cover? Okay, simple enough. And so the basic question we're going to be looking at today is how big a random sample do I need to take of my point set, okay, so that this sample gives a pretty good approximation to the original kind of cardinalities and measures. Okay, so the measured point of view just normalizes, so it's easy to compare because you're just comparing percentages to percentages. Okay, we're saying, okay, if I sample half the points, will all the ranges, still have roughly the same proportion of points? If I sample a tiny fraction of the points, if I sample all the points, can I get away with sampling or anything like this? Yeah. Huh? Yeah, I mean, I left it a little bit ambiguous because there's many questions you can ask, but I think we'll generally be interested in aggressive things like all R and R. Because a single R and R, you can maybe just apply turn off and say, what are the odds I get close? Be more interesting, let's say that we will consider, all possible, where R is all disks in a plane. So it's almost like an infinite number of disks, right? And so somehow it'd be cool if somehow you can address all disks at once with a finite subsample. Okay. All right. So yeah, so this is a little ambiguous. So let's open up a couple of different questions that people ask. Okay. So actually, I guess we'll be looking at two things in particular. One's called an epsilon sample. One's called an epsilon net. They're very similar. So an epsilon sample, I mean, you can maybe guess. Anyone want to guess from the name what it is? Or what? How about this? What's the most natural way, or what are some natural ways to try to figure out if to define similarity? Yeah, yeah. So that will be epsilon sample, and this will be for all ranges simultaneously. So we'll say that Q is an epsilon sample if that percentage value is within epsilon for every range, and it's the for every that we're going to have to work hard to achieve. Okay. Epsilon net is a little bit harder to guess, but is also of interest. Actually, it comes up a lot in learning theory. So something's an epsilon net. Here, your goal is not necessarily to estimate everything correctly. What you want to do is you want to hit every range that has at least an epsilon fraction of the points. So Q is an epsilon net if I wrote the measure is greater than 0 whenever the true measure is greater than or equal to epsilon. So you have to sample at least 1 point from every range. That's sort of a heavy hitter in some sense. Okay, so you want to make sure you hit all of the heavy ranges. A subset of P. So your goal is to take your large P, maybe compress it, but still preserve the measure in one of two meaningful ways. Yeah, this will also be for all. Well, yeah, it's for all R. I guess that was encoded in here for all R with that's greater than or equal to epsilon. Yeah. Well, this is the definition. Uh, so you start with P. P is your true measure, right? It says, there's 10% of the points in this circle and things like this. And now what you want to do, ideally a smaller Q is more valuable. So you want to take a subset, a representative subset of P, right? Which in the case of epsilon net is saying that for every range that's pretty large, it has at least an epsilon fraction of the points, you're getting at least one. Something non-zero. So I guess they use net because you like cast a net and you try to capture all the big things. Maybe the small things slip through. I don't know. But yeah. Okay. And these names are all older than any of us. So yeah. Okay. Okay. So those are two things we'll try to do. And it's more interesting if Q is small. If you just take Q to be P, then that's for free. The question is, how small can we make Q? Okay. Yeah. Perfect. I think that's a next slide. So is this even possible? In other words, can you think of a range space, some family of subsets, where it would be very hard to make an epsilon sample or an epsilon net for a fixed set of points. A non-trivial epsilon net epsilon sample. Yeah.
It's just like one element, like the net, like or just contain one. It's gonna be difficult to get an epsilon sample.
So R is the shape. So if you just have one shape,
The shape is only 1 point, so mu of r is very small.
yeah, okay. So it depends on what you're doing. But at some level, like, okay, so the suggestion was like, oh, what if it was the maybe let's say the family of all singleton sets. So you have n points, but you're only looking at singleton sets. So everyone has measure 1/n. So at some level, that would actually be easy for us because in the first definition, if epsilon's any fixed constant, zero is a fine zero everywhere is fine because the difference between 0 and 1/n is with an epsilon. And here too, nothing is a heavy hitter. So that would actually be okay. So see, all singletons you can actually deal with because you're actually kind of allowed to ignore small things. But what would be one where uh, that would be very hard to deal with? Yeah. What's the entire thing?
Big circle vectors.
Okay, so you have endpoints, and then you have one shape, and that shape contains everything. That too would be not so bad because I just take 1 point, right? Because it contains 100%. If Q just has any 1 point, it'll still be 100%. Yeah.
That example you gave, functions like the subset of points in R2, and then we just consider all sets of closeness. I think that's already
All sets of closeness, like half spaces, circles. Uh, Actually, circles, we're going to be able to get a very interesting non-trivial result. In fact, all of these shapes, natural shapes, will actually get something good. So things that are hard may be unnatural, if that's a hint. Yeah, yeah. All possible subsets. Okay, so if we take R to be the family of all possible subsets, what's going on here? Okay, so right, so at some level, getting any non-trivial subset of P is basically impossible without any assumptions on R if you allow like for all possible shapes. Okay, and you get your set at Q. So let's say you draw your set Q, and you're trying to get like an epsilon sample. Okay, what would be a set that we completely fail to estimate? Yeah. Sorry. Yeah, exactly. So the complement. So the complement, if P is Q is substantially smaller, then the complement will be substantially big enough. But you're estimating 0. Okay. So without some kind of structure on the underlying set, you can't do anything. So whatever we do needs to be actually sensitive uh, to sort of the limited combinatorics of shapes. All right. Does this example make sense? You can do something similar for epsilon nets. I mean, I think the exact same thing works for epsilon nets.
So what is this counterexample to? It shows that you can't have epsilon.
Yeah, so suppose you had an epsilon sample that you had less than 1 minus epsilon times the original point set. Then and you're allowed to pick any range, then we can always pick the range that's the complement of what we took. And there, our sample will think there's no points inside the complement. And it'll estimate 0, even though the complement has true measure epsilon. Yeah, so you can't, because we're at some level, we're trying to estimate everything. Where everything is defined by R. So we're trying to estimate everything in R simultaneously. So if there's no restrictions on R and you lose the slightest bit of information, we'll define R to be the information you lost. Morally. Okay, so good. Right. Now, well, maybe I should hide this. Oh, you've already read it. It's too late. Okay. Yeah.
circle be the same as for a square or a rectangle?
It'll be very similar.
But would the square and the rectangle be like different?
It'll only be slightly different. It'll morally be mostly similar, but we'll see how it unveils. Okay, so what's interesting about a disk over points in a plane is you can't induce all subsets like that, right? So if I arrange 4 points in a square, then there's some subsets I can cover, right? I can cover one of these corners at a time. I can make the circle any size I want, right? So I can cover one square at a time. I can do half the square or something, right? Something like this. Can I do a third? 3 of the corner? Yeah, you could do something like this. What can you not do? Okay, you can't do the diagonal corner, at least if this is drawn correctly. You shouldn't be able to do opposite corners. Okay, so when I have a square that's arranged, points arranged in a square, I can't induce all the subsets that I want to. Right, so there's some things I don't have to worry about. Okay. All right, so good. Okay, so that's the first basic thing about these shapes. That would also hold for rectangles. That would also hold for squares, and we'll kind of articulate that at the end of the lecture in the form of VC dimension. Now, okay, so all right. Now, given a subset of points, I can look at all the subsets it induces over Q, right? So I'm going to use this notation where this is like my big family of sets, and I'm kind of doing some kind of intersection with subset of points, okay? And that's going to be the family of ranges. That's sort of all the intersect. This circle, what subset does it induce over Q? That circle, what subset does it induce over Q? This circle. Okay, so I'll be using this logical and notation for this kind of restriction or overlap or whatever. Okay. Now, okay. Okay, so what we're going to be looking at for a particular range is the growth function. Okay. Say R is your set of circles in a plane or something. And I basically say, how many different subsets can circles induce over a family of endpoints? Okay, so you can put the endpoints anywhere you want, as friendly as you want, and whatever set of circles there are, it can induce some subsets, but not necessarily all subsets over that point set. Okay, and you can choose whatever Q you want. So basically, this is saying, look, for any endpoints, what's the maximum number of kind of distinct subsets that say circles can induce over those points? Squares, rectangles, half spaces, 2 dimensions, 3 dimensions, 4 dimensions. Okay? It's of course at most 2 to the n, but maybe for many interesting shapes, it's actually less. Okay? So let's see. Yeah. Okay, good. Fine. Now, maybe as an example, let's look at like half spaces in the plane. What would be like a growth function for the half spaces? So 2 to the n is always an upper bound. But is there like a better one? Half spaces in the plane. Yeah. So can I argue that there's less than kind of 2 to the n sort of distinct half spaces in this picture? And by distinct, I mean based on the points that they cover. Yeah. Okay, why n squared? Yeah, so some level I can kind of shift this around their equivalent, right? Until they kind of butt into 2 points, which if I had drawn it better, maybe this point and the point that's naturally covered up, that point kind of thing, right? So in 2 dimensions, I can always kind of shift these lines without intersecting until it's tied against 2 points. Okay, so in that sense, all these kind of half spaces are defined by just drawing a line through a pair of points and then choosing one side or the other. Yeah.
Would this also work for any convex shape, or would this have to be like a circle?
Will work for any convex shape. Does it have to be a circle? I should know this. Uh, is there a VC dimension for convex shapes in mode dimension? Uh, my guess it should be probably okay. But don't quote me on that. It's definitely Googleable. Um, okay, what about circles in the plane? Yeah.
Because you can define them through triples.
Yeah, so this circle, I can shrink until it's tightly wrapped around 3 points, and I can't go any further. Okay, so any 3 points will give you a circle. So that'll be like n cubed. Okay. So just in those simple examples, you can start to see that okay, uh, not all subsets are possible, and in both those cases, you have a polynomial growth function. It's not growing exponentially. Exponentially means anything can happen. Once this polynomial is like, oh, there's some structure here. I'm not taking a union bound over everything. All right, so that's the idea. Intervals is even simpler, so I won't even bother. Okay. So at the moment, we're going to characterize kind of the complexity of our shapes by their growth function, which is just given to you. And afterwards, we're going to relate it to this notion called VC dimension. Okay? The randomness just needs the growth part, and then we'll do some combinatorial geometry as time permits. Okay, so good. All right, so let's just do the naive thing. Okay, I have some range. Yeah.
Maybe this was just a misinterpreted project. Are we guaranteed that all the ranges because
So unique is defined by the points. So when I say kind of how many different disks there are in a plane, 2 disks are equivalent if they're covering the same set of points. Yes, yeah. So I'm really saying was based on the underlying points. Yeah. Okay. So let's take the naive thing of just random sampling, right? So then the natural thing is just uniformly sample Q and then see if we do a good job. Yeah, question.
this question, so you mentioned that a particle circle defines what does that kind of indicate that like circles can unique and
Okay, good. What about unions? So first of all, just to be pedantic, R is the set of all disks, not necessarily the unions of all disks. That said, you can take any 2 range spaces, right, and say, what about all the pairwise unions? Unions of one from here and one from the other. And suppose they both have growth functions. Well, at the very least, all the shapes in your union consist of one from here and one from the other. So you at the very least have a growth function that's just multiplying the 2 growth functions together. Right? So there is some amount of composition or intersections and stuff that at least up to shallow depth will also still be bounded, right? So if you're just looking at pairwise unions that's defined by 2 circles, now everything's defined by 6 points, right? Because it's a union of 2 circles, 3 points for each.
that's what leading to the end.
But there I've defined R to only be pairwise unions of circles. So only shapes that consist of 2 circles. So R is not closed under unions. If R was closed under unions, I could just draw a circle around every point and collect any set I want. So that's not what we're saying. R is just the set of all disks. If you take the union of 2 disks, it's not a disk anymore. The definition disk is not in this case. Yeah.
D dimensions, it's the VC dimension is 2D plus 1. Does that make it further?
Yeah, so we will eventually show that something with some VC dimension X will have polynomial growth of exponent x. So yes, so that means convex. So any convex shape in a low dimension will also have this polynomial growth thing going on. Is that Kelly's theorem or something?
I just want to stack exchange.
Oh, okay. There should be a Wikipedia article on it, but it's okay. Okay, that makes sense. So it is important to point out that our power is sort of the proportional or inversely proportional to the limitations we put on R. If R is unrestricted, there's nothing you can do. If R is restricted, then maybe we can take advantage of it. And insofar as these shapes may be natural, these tools may be useful. For example, there's a lot of learning theory based on half-space classifiers, right? And then your sample Q corresponds to learning example, right? Input data. How good is your input data going to generalize things like this, right? So since half spaces do come up naturally in algorithms, we are interested in bounds that are limited to half spaces. Okay. Again, this will come up in a lot of geometry problems and so on and so forth, right? Okay. You can imagine if you want to do clustering, you might want to sample down the points and then work on a smaller set of points and do clustering or something, right? Okay. Because all the clusters are also implicitly circles. Okay, so good. How big should a random sample be? So on and so forth. Okay. Um, where are we? Okay, good. All right, so does the motivation behind growth function make sense? Okay, and so now we're going to try to see if we can get good representative samples of the underlying point set when sort of the range has some kind of limitations on its combinatorics. Okay, so the naive thing is to just sample k points, and I guess the calculations are simpler if you sample as a repetition. Okay, we'll just sample k points, and then we'll just work through. So this is just a naive thing to get us started. Okay. So if we fix a range R, we want to start applying Chernoff, then or how do I model this? I can write this as a sum of indicators. Xi is whether or not the point is in R. Yeah, and the average will give you that measure. So good. So what we're really interested in is something like this. What are the odds that my measure is off by epsilon? Okay. And okay, I'm just substituting in. Okay. And there's quietly an additive Chernoff bound sitting at the bottom of that slide. Okay. So I don't know if it might be too small, but okay. So when you start applying that Chernoff bound, right? I'm taking the average over k things, they're all between 0 and 1. That means I'm looking at e to negative 2 epsilon squared k. I'm using k instead of n because n is reserved for the number of original points. Okay. The 2 is just coming from bigger and smaller. Okay, good. So nothing special. This is just applying the additive Chernoff bound to a single range. Nothing particular to range spaces. Okay. Now, how many ranges do we effectively need to worry about? It is true that there's all this in a plane or something, right? But we're really only interested in the subsets they induce over the original point set. So what would that be? So this is the number of ranges, kind of how many different subsets it induces over the set of points. RMP will collapse identical subsets. It will be the growth. That's all. Okay. So if I want to start trying to take the union bound over, effectively, we only have to worry about this many actually distinct ranges, then what should I start setting k to be?
Log divided by 2 epsilon squared.
Yeah, so we just want to make that e to the negative 2 epsilon squared look something like 1 over g of p or something, right? So we should put a divided by epsilon squared to cancel out the epsilon squares, and then a log of G of P. That must be down here then. Right, so we have something like this. You start setting that. Probably it's not an epsilon sample. It's a probability that some range has error bigger than epsilon. G of P times this. And I'm going to say 1/2. If we're just trying to get it with constant probability, if you want higher probability, you just crank it up. Okay. All right, so that's just kind of plugging in. And by now, you guys have probably done this plugging in a bit yourself. Okay, I mean, by now you know if you want a union bound over n things, put in a log of n, right? Okay, so good. All right, any questions? So that's sort of the naive, what you would normally get without taking on any advantage beyond this GFP. Okay, yeah.
Just to clarify, so if my part should just be like the number of beds are that enter segment.
Yeah. It's a little compressed, but what the RMP is really doing is it's highlighting the fact I'm interested in which subsets it induces over P, so that two disks are really equivalent if they have this contain the same points. Okay. All right, so that's just a union bound, and we know there's only n cubed circles, so we can just take a union bound over n cubed thing. So I only need log n points. Okay, good. All right, so that's what we showed. If you put log of n cubed over epsilon squared, that'll work for disks in a plane. That'll give an epsilon sample. If you want to do an epsilon net, slightly different calculations, but the epsilon squared goes down to epsilon. Okay, we won't do that. And now the question is, can you do better? Okay. All right, then let's have a vote. Okay. So we have at least one vote for no. And then you can also not vote. All right, so who's not? So you think you can do better, not do better, or you're not voting? Okay, so who's not voting? 1, 2, 3, 4, 5, 6, 7. Even the people who not vote, like barely not vote. Okay, who thinks we can do better? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, maybe 18. Hey, who doesn't think we can do better? 1, 2, 3, 4, 5, 6, 7. Is that 2 votes from Borna? 8, 9, 10, 11, 12. Okay. 12, counting only 1 vote for Borna. I'll put an exclamation mark for his enthusiasm. Okay. Those who voted no, or those who voted yes, why? Yeah, well, okay, so for those who voted no, do you think we're gonna maybe do the turnoff bound finally? Okay. All right, so let's try to do better. Okay. Okay. Does anyone want to try to guess? Actually, this is a little bit hard. So suppose my growth function looks something like g of n is big O of n to the d or something, some parameter d. Does anyone want to guess what we can get? D over epsilon squared, epsilon. Any other guesses? Okay, so actually the original version is a little bit complicated. You're going to choose any k so that k is bigger than log of g of 2k. Okay, what the hell does that mean? That means if it is a polynomial, then d log d over epsilon squared is enough. Okay, so let's go back to circles for a moment. Circles is n cubed. Okay, so this is saying you only need 3 over epsilon squared points to estimate the proportion of points of every circle simultaneous up to epsilon factor. So it's basically just dependent on epsilon. 3 over epsilon squared. It was very strong. Completely got rid of. So what's sort of amazing about this? There's some variable missing. There's no n. It's entirely a function of the complexity of the underlying range space. There's no dependence on n. Yeah. You can see why this might get exciting from like a learning theory point of view if you want to kind of generalize to all possible examples or something. Then n is not finite. Yeah.
Random sampling, or is this like saying that there exists a sampling?
And we'll do an algorithm. In fact, anyone want to guess the algorithm? Yeah, we're just going to uniformly sample. It just turns out you can get way lower. Okay. And then epsilon sample theorem, anyone want to guess? Or epsilon net. If you just want epsilon net, that's the weaker one. You just want to hit all the heavy hitters.
Same thing over.
Yeah, this is guessable. This will be the same thing, but just one epsilon.
There's no D in the outlet.
Yeah, so that's either a typo or just some kind of freak thing. But the great news is that one way or another is going to be your homework to do this one, so you can sort it out. Yeah. Okay.
Just include the typo and say it was a typo so we can do ourselves.
No. If we start playing this game of like, it's okay because Ken made a mistake, like it will never end. Like the whole class loses all its integrity and like you guys are an error correcting code or else nothing will work. Okay. All right. Okay, but you can do one epsilon is the key point with the log between friends anyway. That also you're not allowed to put on the test. Okay, good. All right. Okay, so let's try to do this, and we are going to do a uniform sample. Okay, so we're going to have some sample, and we're just gonna. The question is, how can we get the size as small?
Same algorithm.
Exactly. Yeah. No, it's the exact same algorithm. And it's also like oblivious to the shapes and stuff, right? It's not like saying, oh, worry about that circle, not worry about this circle. It's not doing any. Okay. So I'm going to sample k points. Okay. And I'll set up as an event. This is the bad event I want to avoid. The probability I'm off by epsilon for some range. Okay. Now the proof has a very clever twist. I don't know if anyone wants to try to guess this twist before I reveal it in a moment.
What type of twist is
It's I don't know. It's like 2.5 twists on the twist scale. Yeah.
They're independent.
No, they are independent. The algorithm doesn't change. The algorithm hasn't changed. It's just independent sample. So the other thing we're going to do. Let's see if it's actually on this slide. Oh, okay. Twist isn't here yet. Okay. We want to show that this event occurs only a small amount of time. Okay, fine. Twist is coming up. Okay. All right. So your first sample k points. Okay. Now this isn't part of the algorithm. This is part of the analysis. We are going to. Thought this would work. That didn't work. Oh, one sec. Okay, good. I'm going to sample k more points. Okay, we're going to do a second sample. Okay, and now I'm going to define a slightly different event. So I'm going to let mu1 be the measure induced by the first sample, and I'll let mu2 be the measure induced by the second sample. Instead of writing mu of q1, I'm just going to write mu1. Instead of mu of q2, I'm going to write mu2. Okay, and this is saying, okay, what are the odds that these two samples disagree on a single range? Okay. Good. We're still only interested in A. The algorithm only actually samples Q1 and returns it. But somehow we're going to find it helpful to imagine sampling a second set of K points. Okay. At some level, that's why this G of 2K sort of comes into the. Okay. And here's another clever step. Is it on this slide? Yes. Well, like one more event. It's the event that A and B happens. Okay. Which yeah, that means that for well, okay, maybe it's not exactly A and B. That's not formally correct. I really want to say that for the same range R, uh, both this is off by epsilon and this is off by epsilon over 2. Okay? That's actually not formally A and B because A and B would allow for different R's. Okay, now I know why I didn't have that and I shouldn't have added it this morning. Okay, good. All right, good. All right, so here's C is actually just a proxy uh, for this claim. The claim is that the probability of A is less than equal to 2 times the probability of B. Okay, does anyone want to guess how to do this? Some triangle inequality will actually end up playing in, but we need one step to get there, so keep that in mind. Okay, so the probability of B, okay, this is going to be greater than, so this event C, which is like 2 things happen for the same range, is just harder than 1 thing happening for the range, right? So this is bigger than probability of C, okay? And C encapsulates A. This seems like such a weird thing to do. Something like this, okay? And now I can break this down as the probability of C given A times the probability of A. Okay. So it seems like we did nothing, but somehow this is going to be very helpful. So if I can just show that this thing is like greater than or equal to 1/2, then I'll be happy. Okay. Okay, so let's look at probability of C given A. So that means that there's some range R where the measure is off. Okay, by epsilon. And now I want to say, what are the odds that mu2 and mu1 are off by epsilon over 2? Okay, so really, all we need to show is this, right? Because this is already given. So you have some range where this is given. Now you want to show for that range with constant probability, the 2 will disagree. Why? Even intuitively, there's an explanation without worrying about the calculations. Okay, so what about this? Let's look at like, what's the probability that mu2 r minus the original mu of r is, say, bigger than epsilon over 2? Well, this just goes back to that first Chernoff calculation we did for a single range, which will actually be e to the negative something something, and you already have the epsilon squared in k, right? So this is easily less than 1/2. It's really like 1 over log of the growth rate and stuff like this, or 1 over the growth rate or something. Okay, so this is definitely less than half. Now, if that's the case, so what's really going on, right? So in event A, one range is way off on its thing, right? And event 2 says that one range has disagreeing estimates. Now, any single range is almost definitely very accurate. But event A, one of the ranges is very inaccurate. But if that for that range, the other one does it accurately. If one does it inaccurately, one does it accurately, then they disagree. So that would just play out in a triangle inequality. And there's a reason why we need the epsilon over 2 to kind of make the math work. But this is at least, okay, the error from the first sample minus the error from the second sample. And if you're telling me that the error from the first sample is really big, it was pretty good probability the error from the second sample is small like we expect, then you'll get your epsilon over 2. So A is really the unlikely event. Once A happens, it's actually very likely that the other one will disagree with A because the other one is likely to be correct. Okay, makes sense. So somehow, somehow, some like nothing happened, but something happened. Right? Feels like a magic trick. Okay, good. So now that I know that A is bounded by B, B is just a probability that two different samples disagree. Now I just have to get some bound for this. Okay. Any ideas? I guess the only hint I can offer is at some level, we're really trying to replace a log n with log of g of 2k. Somewhere 2k needs to enter the picture. Yeah.
You consider like the union of the two and like that approximation.
Exactly. So okay. So definitely 2k is going to come from the fact that q1 sampling k points and q2 sampling 2 points. So together you have 2k points. That's definitely an important observation. I'm only egging you on because you're actually taking a step in the right direction. Is there some way? Is there a different way to kind of reimagine q1 q2? Like I would really like to take the range somehow. It would be very nice, right? If I could argue that I only have to take a union bound over g of 2k points instead of g of n points, right? So if I can somehow argue that there's only implicitly, if it circles 2k cubed circles to worry about instead of n cubed. Yeah. Uh, can you consider when q1 q2 are disjoint? Um, yeah, I think that's not going to help us too much either way. Yeah.
The 2k points are representative of the overall.
Can we argue that the 2k points are representative of the overall? I think that's a little bit cheating. To do that, we'd have to kind of redo this whole proof all over again, or some level. The difference isn't just a factor. We're trying to go from log n to log g of 2k, not just c of a factor of 2. So I think we'll need something stronger. Okay, so so one way to generate a sample q1 q2 is a sample k then sample k. What's another way? Or take turns 1 1 1 1. Okay, what's another way? Sample 2k. Okay, so we're going to generate as follows. First, we're going to sample 2k points q0. What does that do for us? Remember, all we're analyzing now is what are the odds that they disagree on some range. Okay, so I'm going to sample 2k points and then I'm going to divide it in half. That'll give me the same. That's a different way to generate two samples of size k, right? But what does this approach do for us? I just want to know if q1 and q2 disagree on some range. Yeah. Well, I mean, q0 is allowed to have points that are repeating. Yeah. Why? So at some level, I want to know if q1 and q2 will disagree on some range, right? And originally, I'm worried about all g of n ranges. But if I do it this way, how many ranges am I worried about? G of 2k, right? Because once you get down to the 2k, now you have to distinguish much fewer shapes, right? Just subsampling down to 2k first already collapses the number of ranges you have to worry about. Yeah, there's been like several twists along the way. The first twist was like the second sample, and then yeah. Uh yeah, I'll come up with a better one for you next week. Okay, so let's look at the probability of B. Okay. Now, what we can do, to do it formally, you'll condition on Q0 first, right? What's the probability of B given one particular Q0, another particular Q0, whatever, right? And Okay, we can just bound that by the worst possible Q0. Who cares what the Q0 is? Okay, yeah.
What do you like the probability of B given Q0? Do you mean like the probability of like over like different partitions?
Yeah. So maybe I should have written this more formally as like little q or something. The probability that's given that's equal to a particular partition. Yeah, it's a little. The metaphor. Okay. Yeah. So conditional on the particular initial set Q. Q0 is the initial set of 2K. So first you sample 2K, and then conditional on that, what's the odds you make a mistake? And now if we can show that no matter what the initial thing was, we can get a good bound. That's really what we're doing. No matter what the initial sample, we're going to get some bound. Okay, and then we'll be happy. Okay, but we already got the intuition. How many sets are induced by Q? How many subsets are induced by Q0? G of 2K. So now we just do the same thing, but we only have to union bound over these sets. Okay? So we apply additive Chernoff, and just for that choice, where we now have log G of 2K, times some constant, you'll get something inversely proportional to G of 2K. It's just there for convenience. Okay. And now, you start taking a union bound over all of these G of 2K ranges, and so you have to be a little bit more careful, but you know that this one will be within epsilon over 4, and then also the second measure will be within epsilon over 4. So both of them will be accurate on all G of 2K ranges, very accurate now, epsilon over 4, with good probability. So now for all ranges, you just do some triangle inequality thing, right? So you subtract out these two, right? The difference between the two is the sum of, at most, the sum of differences from the true, where true is actually given by Q0, epsilon over epsilon 4, and you get epsilon over 2. Okay, but the real thing is using Q0 to get it down to effectively 2K points. Yeah, it's very cute. Remember, the original algorithm does not do that. It just samples K points. It's only in the analysis. Okay, you do this for all the ranges, and yeah. Okay, so there's your thing. All right, sounds good.
There's no easy way to do it. You have to like duplicate it.
Well, the algorithm is as simple as possible. It's just sampling K points.
Unless there's no easier way to.
Yeah, there is no easier way that I know of to do this, and I was really hoping this would impress you, and I'm a little bummed out. I think this is great. Yeah. Uh, I think here I just wrote 3/4. Look, by the time you get to here, you can union bound over all the shapes, and I could have made that 8/16. I could have made it bigger, whatever I wanted, just by increasing the constant inside in the point set. Yeah. And then I just chose some conservative numbers, which I'm sure upon scrutiny weren't conservative enough. Yeah. Okay. All right, that okay? Okay, good. So that's the epsilon sample theorem. And then for homework, we have the epsilon net theorem, including figuring out whether or not yeah, anyway. But the obviously epsilon net theorem, you also want to take advantage of this double sampling, reducing to 2K trick. But then some things will change because you only worry about hitting the heavy hitters instead of estimating everything was additive turnoff or something. Okay, so you'll do some things morally similar, but then some interesting things will still need to change. Yeah, so it should force you to go through all the motions. Okay, good. So let's talk a little bit about VC dimension. Okay, because that's one way to bound this growth. Okay, so VC dimension. Okay, so you need some definitions. So first, we'll say that a range shatters a point set if it induces all possible subsets. Okay, and okay, and okay, so the VC dimension is the maximum cardinality of any set that can be shattered by the range space. Okay. All right, so good. So it's just, that means like for circles, it's going to be something like 3. So once you start getting to 4 points, it gets harder to induce all subsets.
It's just the numbers.
Size of Q is number of points. Yeah, overall subsets Q of T. Okay, so something like points and intervals. Does anyone want to take a stab at the VC dimension? So if there was 2 points, can you shatter it? Okay, and then if it was 3 points, can you shatter it? I think I have 3 drawn up. So 3 points, it's impossible to get these two together. So, oh, maybe it's either a typo or of the form min size of Q does not shatter. Should be a worse typo. Anyway, we're only off by 1. Okay. Points and disks in the space plane. Anyone want to guess and get it right up to plus or minus 1? Okay, I got 4. I think it's actually like the smallest you can't shatter or something. Because it's very hard to shatter these 4 points. Maybe it's 1 plus. Somehow I'm off by 1 in my depth. I have my notes. We can only hope they're correct. Sorry? No, I'm saying you can't shatter those 4 points, but somehow I've my definition is off by 1. Maybe it's 1 plus. Okay, whatever. We're off by 1. Okay, so we can't capture this donut with a circle. Okay, fine. And then half spaces, I'll fix my notes tomorrow. For half spaces, yeah, I guess we don't know what the right definition is. But in D dimensions, it'll be size of Q. So it's a dimension plus 2, and that's coming from something called Radon's theorem. Or no, what am I saying? Sorry. Given Radon's theorem, that if you have 4 points, right, for any 4 points, you can always partition it so that the convex hull of 2 different sets are non-empty. That's how you prove that. Okay. So what's that? Maybe these are all off by 1. You can do 3, but you can't do 4. Maybe this should be 3. Okay. They're all hiding in a big O in our theorems, but sometimes I get a little too theoretical. Okay, whatever. So half spaces also have some low VC dimension. What I want to focus on is yeah, okay, so so I think I was off by 1 in the example. I think the definition was correct and it should have been n squared for intervals, n cubed for disks. And somewhere I think I got confused with something called shattering dimension and I made some slides and I forgot to update something. Okay, that's fine. All right, so but what I really want to do is Sauer's lemma. If some range space has VC dimension D, then it has polynomial growth n to the D. That's maybe not too surprising because you already kind of saw directly that disks have n cubed and intervals have n squared, right? But okay, so that's what we'll do in the last 5 minutes. Okay, this is not so randomized. This is just some discrete geometry. Okay, so we're gonna directly prove really this thing, that the growth is bounded by this sum from I equals 0 to D of n choose I. So all subsets size 1, size 2, size 3, size 4, size 5, up to D. Okay, and that's less than or equal to n to the d. Okay. We're going to do this by some kind of induction. What are the base cases? So, or what are the dimensions? One is the VC dimension, so VC dimension equals 1 or even 0. What's another base case? N. N will be the other base case. So maybe in the interest of time. So if n is 0, I guess g of n is 0, and that's if you plug in f of d 0. If the VC dimension is 0, then you can induce it with one shape or something. I think we're not counting empty set or something, and that's f0. Okay. Okay, so base case are not too interesting. Let's do the fun part. Okay, so in the interesting case, you have some VC dimension that's non-zero and a non-zero number of points. Okay, so we're going to try to use induction. So the natural thing to do is to try to remove a point. Okay, so we'll just pick some point, and then we'll remove it, right? And now you have all these ranges obtained by removing that point. Okay, so that's one way to try to whittle it down. So, okay, you're going to hate my notation. You'll see in a moment. I'm going to write r to the p will be the ranges obtained by removing 1 point from each range. Okay, that means some ranges may collapse to become the same. Okay, and then they'll only count as 1. They don't count as 2. Okay, so good. Now, what do we know about the VC dimension of this set? It's at most what? I think it's just at most d, because you know the VC dimension is kind of like the worst or the maximum set, and if that point's not even in the maximum set, then it's nothing. So it's at most d. We can't really say that the VC dimension has gone down or anything, so that won't go down. Just number of points has gone down. Okay. So by induction, that's not right. Sorry. By induction, this thing should be at most f d n minus 1. Okay. I think that typo is going to come up on the next slide, which is copying this, but we'll see. Okay. Now, okay, it'd be very nice to be like, oh, the number of ranges is equal to the number of range to the p, and that's at most this, and we're basically done. But of course, it's not, right? In general, we may have more ranges originally than left after removing that point. And so, sort of intuitively, how might we characterize or kind of describe this difference? So r to the p is obtained by removing p from every range. And the number of ranges, distinct ranges, might go down. So how can I try to characterize this difference? It's at most times 2 because yeah, so basically, you know, we may be double counting if a range down below had both a version with p and without p up above. Okay, so okay, no. Okay, so let's look at those double counted ranges. Okay, so they're all the ranges that don't have p in it, but both with p and not p are in R. Okay, so these are all a subset of. They're all subsets. They don't. None of them have p, and they're just the ones that are double counted. Okay? Now, once you have that, now you'll account for everything, right? So first you remove all the things, and you get a set of ranges, but you're kind of leaving out a difference equal to the ones that sort of get double counted, or kind of have two different parents. Okay, these are sort of the double counting ones, and then the original thing. Okay. Okay. Now. Okay. Good. Now look at these double counting ranges. What can we say about their VC dimension? Why? Yeah, okay, so I think our definition originally was correct. So if this has like VC dimension 9, right, and these are all the ranges where originally, in the original range space, I have that set both with and without P. Okay, so if I'm able to shatter a set of 9 points, then the original R can shatter a set of those 9 plus P, because these are all the things that kind of have versions with and without P. Okay, so that means the VC dimension is at most D minus 1. So that's critical. Okay, anything down here? No. Okay, so now we've okay, it's going to be just on time. We've sort of divided R into 2 sets. They each have n minus 1 points, or they're both over n minus 1 points, but one has VC dimension D and one has VC dimension D minus 1. Okay, so good. We have like that. That's not too surprising. And then just by induction, here's VC dimension D minus 1 n minus 1 points. And then this is sort of the original D at minus 1 points, because we couldn't say anything about the VC dimension of that first set. And if you start plugging in, I mean, this identity is sort of chosen to satisfy this recursion. Okay, so if you plug in these things, and then, okay, now how do I think about this? So this is summing up a subset of n minus 1 points for all sizes from 0 to D minus 1, sets of size 1, sets of size 2, sets of size 3. And it's saying, okay, out of n minus 1 points, from all sets of size 0 to D, 1, 1, 1, 1, 1. So how can I collapse that in Y? Who can give me like a description? You kind of know what the end goal is, but why? Okay, I don't know what the name of anything is. So what? No, who can give me like a description? Okay, well, so the next line is going to be. Okay, that's no fun. A little. Where did this I minus 1? Yeah, maybe this should be a 1 now. Something like this. Okay, but what's one way to think about it? Or what's a description of, I guess, Pascal's identity? No, come on. So one of these sums, you can think of this as, taking. So this is taking up to D minus 1, right? And then you can add in P or not add in P. So this can get you all the sets that don't use P. This can get you sets using P. Okay. Anyway, so in the end, you should get what you're looking for, like this. Okay, that's fine. But that's all I wanted someone to say is to interpret the sum sort of combinatorial, right? Okay, good. So that's it. So that's how you get this Sauer's lemma. You have this. It's just a counting. It's a combinatorial identity. But the really cute thing is that the double counted ranges, the VC dimension goes down by 1, and that gets you this critical D minus 1, and that's how you get this n to the D bound. Okay, it's just a math thing, but that's where VC dimension ties into growth rate. Okay, thank you.